point, because we want to be, I mean, you can see below in the next section, we're jumping into the calculus stuff tomorrow. So we want to be able to take our knowledge of the pre-calc aspects of inverse trig and use it to help us understand the calculus. I will follow that up by saying that there is no aspect of this unit that requires new calculus instruction. All right, all the calculus that you need to know in this unit, you already know. All the calculus you need to know for the remainder of this course, you already know. All right, so it's a matter of just using it in different ways. So that's kind of a nice thing to hear, I think. All right, so arc cosine. Well, the cosine ratio, thinking of SOHCAHTOA, would be adjacent over hypotenuse. So what I'm going to do is draw a triangle, a right triangle. I'm going to chuck in a theta there to give myself a reference angle. I'm going to indicate my adjacent side is 4 and my hypotenuse is 5. All right, right on back to Algebra 1. All right, what's my missing side? 3. A little Pythagorean triple action going on there. All right, now this is the important thing to remember, and honestly, it's the most commonly missed concept. Arc cosine, arc sine, arc tangent, arc whatever, the result of that is always some angle theta. All right, so what they're telling us here is that theta is equal to the arc cosine of 4/5. All right, you could always represent an angle as an inverse trig function of some ratio. All right, so instead of writing 60 degrees, I could write arc cosine of pi over 3. All right, you could always write it as an inverse trig function. All right, so that triangle essentially represents the arc cosine of 4/5. What I want is the sine of theta, which indirectly means that I want the sine of that triangle. Poor quality theta. Sine of theta is the opposite side over the hypotenuse. The opposite side is 3, the hypotenuse is 5, so 3 over 5. So the sine of that triangle, opposite over hypotenuse 3/5, really directly means the sine of the arc cosine of 4/5. So I just discovered without using a calculator that the appropriate ratio is 3 over 5. Now, you could have, you'd be correct in doing this on a quiz, test, whatever. Type in the sine of the arc cosine of 4/5. The calculator will spit out 0.6. You can math frac it, get the 3/5 and call it a day. But then when you look at the next example, so anyway, just to again reiterate, whenever you're looking to find the sine of something, that something is a theta. And this is something that people have lost sight of repeatedly. And it's kind of a problem because it's going to sound harsh. It symbolizes the fundamental lack of understanding of trigonometry. And so, yeah, it sounds terrible when I say it that way, but maybe it just symbolizes that. Maybe it's not like representative of you individually. It just looks like you don't understand trigonometry, right? So if you look at this and think, like if I ask you to find the derivative, if you were to think product rule, because I have a sign and I have a set of parentheses, I think you're probably too rigid in your thinking. All right, and so that's you want to be more flexible, more malleable as you move forward in life, because it can't always be if I see this, then I do that. All right, because I mean, yeah, there's time and place for that. Like a stop sign would be a pretty good indication of that sort of idea, but we know that parentheses don't just mean multiplication. All right, they can mean a lot of things. right? So in this case, it means the sine of the arc cosine of x, right? So I would not, if I were to find the derivative here, I would not use the product rule with the sine, because sine without something contained within the sine is meaningless, all right? That would be like if I were to give you an expression with just a plus sign, all right? That sign is like plus. It's an operation. It needs to be operating on something, all right? So whenever you see sine, cosine, tangent, you should be thinking sine, cosine, or tangent of what? That of what should be an angle, right? Whether that angle's in degrees or radians, that's immaterial. It's really just a matter of it is an angle. It is something you're taking the sine, cosine, or tangent of, all right? So now that we've kind of beat that to death, I would establish here that the theta is represented by the arc cosine of x. All right, so I would just kind of jot that down off on the side here. Theta is equal to the arc cosine of x, for quality S. So then the next layer of this, what is the arc cosine of? Because again, the parentheses don't mean multiplication. They mean that we're taking the arc cosine of something. All right, so this is a ratio. All right, that ratio is the cosine ratio, right? Specifically adjacent over hypotenuse. All right, so you look at the x and you say, I don't see a fraction there. Well, anytime you see a number, you see a fraction. It's just a fraction over 1. All right, so the adjacent side is x, the hypotenuse is 1. All right, so all of that was covered in the span of like 15 seconds yesterday. I felt like it may have deserved a little bit more attention. All right, so to find the missing side, a little Pythagorean theorem. With a little bit more experience, you could do this in your head, but for now, we'll just not. We'll just say x squared plus b squared is equal to 1 squared. B squared would be 1 minus x squared, making the b value the principal square root, or the positive square root, of 1 minus x squared. All right, I wouldn't care about the negative in this case because we're talking about a length of a side, and we're not talking about it in a Cartesian plane. We're not talking about it on an xy coordinate axis, so direction is not important. All right, so square root of 1 minus x squared. All right, so one thing that we did discuss yesterday in great detail was the idea that when you're finding the sine of theta, that theta is represented by the triangle, right? So theta, every aspect of theta is represented by the triangle, right? You can get 6 trig ratios. So if the question said tangent or secant or cosecant, it doesn't matter. I can get what I need from this triangle because there are 6 possible ratios. I have 3 sides. I can create any of those 6 ratios. What I need is the sine ratio, which is the opposite side over the hypotenuse. The opposite side is the square root of 1 minus x squared. The hypotenuse is 1, and so therefore this boils down to the square root of 1 minus x squared. All right. Now, motivation. You can take a look at this, all of this work, and you say, why on earth would I want to do any of this? My answer to you is, I think, fairly simple. If you had to take the derivative of this, right, the derivative would involve the chain rule because you have a function inside of another function. Do you know what the derivative of the arc cosine of x is? Maybe. Most likely not. All right. Can you figure out what the derivative of the square root of 1 minus x squared is? Yes. All right. So one form can't work with necessarily. The other form definitely you can. All right. So that's really a the main motivation behind this is the ability to convert from one form into another, right? You'll find actually, depending on how much calculus you do before it's all over, let's say you take Calc 2, Calc 3, you'll find more often than not you're converting from the algebraic form into the trig form because it'll turn out that the trig form is more convenient.
Why did we do use the cosine ratio for x if it's arc cosine?
Because when you're taking the arc cosine, you're taking the arc cosine of the cosine ratio to give you an angle, right? So I'll just off on the side here, just jot down a separate calculation, operation. You have theta is equal to the arc cosine of x. If I were to take the cosine of theta of both sides, or cosine of both sides, that would give us cosine of theta on the left. Cosine and arc cosine would cancel on the right, giving you just the x. And since we know that cosine is adjacent over hypotenuse, a over h would be x over 1. All right? So all of that was behind the scenes. All right, so the next one, secant of the arc tangent of 3x. So you'd be right in thinking, well, I don't want to take the derivative of that. Let's see what it would look like in algebraic form. So we have a theta. All right, that theta is the arctangent of 3x. Dang, this pen. They promised me an Apple Pencil last year. The school, yeah. So I bought this cheap knockoff of an Apple Pencil for $25. It gets the job done mostly, but you can see that it doesn't always. What can you do? I would love a pencil that had apples on it. Yeah. So tangent ratio is opposite over adjacent. So 3x would be my opposite side. The adjacent side would be 1. Pythagorean Theorem. This one's a little easier because when you have the two legs, you're squaring them, adding them together, and just throwing a radical over them. Right? So it's when you have the hypotenuse in one of the legs, it's a little bit of a different story. So 1 plus 9x squared is what you're going to end up with here. All right, so in number 7, if you looked at that as like an unnecessary amount of work just to kind of clean it up into a more convenient form, I would agree with that, but if your algebra skills kind of improve to the point where you can construct your triangle without having to show all the side work, then it starts getting more convenient to do it this way. All right. So the secant ratio, hypotenuse over adjacent, it's a reciprocal of cosine. So 1 over the square root, that would be the cosine ratio. The square root of 1 plus 9x squared over 1, which is the same as square root of 1 plus 9x squared. Again, if I needed to take the derivative of this, pretty not bad. All right. Bless you. But let's see if we can discover some rules for inverse trig and derivatives. All right. We're going to use implicit differentiation, but a little bit of a twist on it. All right. And it's kind of like if you kind of think back to when we were learning about trig derivatives to begin with, it was like, all right, you learn one or two of them, and then once you learned one or two of them, you pretty much understood how to do all the remaining ones. It's just a matter of doing it. It's the same idea here. It's going to be the same process over and over again. So I'll show you a couple cases, and then I'll give you some time to practice on your own. All right. So d arc sine of u dx. All right. So that's saying find the derivative of the function arc sine of u dx. All right. Now we're calling it u because u is a function of x. But what I'm going to also do is just kind of get a little crazy with this and call that d theta dx. Instead of dy dx, we'll go d theta dx. Because again, arc sine, the result of an arc function is some measure of theta. Right? So it makes sense, instead of calling it y, let's call it theta. You could call it y if you want, but let's not. All right? So I'm going to make a note here that theta is equal to the arc sine of u. Bring it in a little bit. Now, this is the problem. I don't know the derivative of the arc sine of u. All right? But I do know the derivative of the sine function. So let's work off of that. Let's take the sine of both sides of the function. So sine of theta would be equal to the sine of the arc sine of u. All right, so really not much different than what we did before, just we're working in general terms here. So instead of x or 3 or just some numerical value, it's u and theta. All right, so we have sine of theta would be equal to u. All right, now the sine ratio, again, is opposite over hypotenuse, so I can make a note of that. Or quality O. I could even draw the triangle. All right, so the u is an implied u over 1. Right, so the opposite side would be u. The hypotenuse would be 1. All right, I'm going to kind of steal the work that we did before, because arc cosine of u, when we knew one side was x and the hypotenuse is 1, the other side ended up being the square root of 1 minus x squared. So there's no reason to think, bless you, that this would be any different than the square root of 1 minus u squared. So now I need to find the derivative of this with respect to x. That's the implicit part of it. All right. So let's start off with the left-hand side. What's the derivative of sine of theta? Cosine of theta. All right. Now it's with respect to x. So I have to take the derivative of my inner function. And this is the kooky part. This is the implicit part. I'm going to multiply by, if I'm taking the derivative with respect to x, I have to take the derivative of that theta with respect to x. So what should I write? D theta dx. It was like the idea when we were first learning about implicit, where it was like, all right, if you're taking the derivative of an x term, you do that the way you normally would. But if you're taking the derivative of anything other than an x, like a y, you slap on a dy dx. Well, it's theta, but still it's taking on the role of y. So we're slapping on a d theta dx. All right. On the right-hand side, under normal circumstances, if I had a standalone variable, its derivative would be 1, but it's not an x, right? So I slap on a what? Du dx. Highlight it in blue first. So we're like pretty much there. It just doesn't seem like we would be. I mean, it looks like a mess. But we want to get d theta dx, right? So let's get that cosine of theta over to the other side. I'm just going to divide that out. D theta dx would be equal to 1 over cosine, which you could write as secant if you want, times du dx. So I'll write it as secant x times du dx. Oh, theta, sorry. But you look at it and say, well, it's got thetas in it, it's got x's, it's got u's, it can't possibly be a complete answer. But maybe you just want it to be, so you're like, all right, it's fine, let's move on. But we can change the secant of theta, because the secant ratio is what? Sine is opposite over hypotenuse, so it's secant. Hypotenuse over adjacent. All right. So if we just make that quick substitution, we have 1 over the square root of 1 minus u squared times du dx. All right. Now, I mean, if you're anything like me, and if you are, I feel sorry for you. But if you are, you got to be like, why? What was the point in all that? And the short answer is, well, the point in all of that is not to do that whole process every time. Like, I mean, I would never expect, it would be like using the limit definition of a derivative every single time, even for the more complicated chain rule questions from the last unit. It's like overkill, right? What we were doing here was inventing a rule. We were creating a rule that gets us directly from the arc sine of u to a final answer. Because if you just look at what we have here, it's just telling us that as long as I know what u is, I plug it into this bad boy and I have my derivative. All right, so if I had arc sine of x, 1 over the square root of 1 minus x squared, but then I would just multiply by du dx, the derivative of that x, which would be 1. All right, so all we're doing is plugging in rather than deriving it every single time. All right, but this shows you where that information comes from. And it also shows you that like everything that you needed to know was already stuff that you knew, right? That's what I was saying yesterday. Like your calculus knowledge was sufficient. Like there's nothing new in here, right? All we were doing is creating a new rule for a function that you've already seen before, right? So that's one rule. Let's do arc tangent, and then I'll set you free for the foreseeable future. Well, that algebraically is how it played out.
Secant.
Yeah, the hypotenuse over adjacent.
So, if you wanted to like just jump to that step, isn't your u, you wouldn't plug in u, right? Because isn't our u opposite over hypotenuse?
Well, you would plug in whatever the u is from the original function, and then you'd plug in the derivative of whatever that u is. So if I had something like x squared, I'd plug in an x squared where I have the u, and then I'd plug in a 2x where I have the du dx. And then that would be it. All right. Now, that is going to require a little bit of memorization / typing stuff into your calculator. But, yeah, I mean, the trade-off is doing all this work, I guess.
But the benefits
But the benefits are too ghastly to consider. Anyway, the tangent. We have theta is equal to the arctan of u. Now again, we don't know what the derivative of arctangent of u is, but we do know what the derivative of tangent of u is. So we make that adjustment. We take the tangent of both sides. So we get tangent of theta is equal to u. The tangent ratio is opposite over adjacent, so I could draw my triangle. Understood denominator of 1, so that gives me my adjacent side of 1. Square both sides, add them together, throw a radical over it. You get your hypotenuse of 1 plus u squared. So then I'm going to take the derivative of both sides with respect to x. So what's the derivative of tangent of theta? Secant squared theta. It never went away. Nice. Now I'm going to multiply it by what? d theta dx. The derivative of u, 1 times du dx. All right. Again, our goal here is to solve for d theta dx. Because again, this whole biggity bangity boom here. That arctan of u is the same as the theta. Right? Inverse trig functions always give you a result of theta. Always give you an angle. All right, so I'm going to divide out the secant squared of theta. Streamline it a little bit. D theta dx, instead of just rewriting it just to change it, I can take my 1 over secant squared and make that a what?
Cosine squared.
Cosine squared. Now cosine is adjacent over hypotenuse, but I want cosine squared. So adjacent over hypotenuse squared. Or adjacent squared over hypotenuse squared. So here's my adjacent. Here's my hypotenuse. If I square my adjacent, square the 1, I get a 1. Square my hypotenuse, just
That's very close to u squared.
times du dx. And that's my rule for arctangent. So now if I'm given any problem involving an arctangent, if I need to find the derivative of that, whatever the u is, the u gets chucked in here, its derivative gets multiplied at the end. Alternative forms, a very slight difference, but people tend to like it. I'll start to write it on the next page, but instead of writing this as du dx, you could also write it as u prime, and then just pop it into the numerator so that you have one concise fraction. All right, so that's just something to think about. All right, but let's flip to the next page, because I'm just basically going to ask you to try the remaining problems on this page, and then we'll debrief on that at the end of class.